In Chapter 8, we're dealing with two populations. And we're going to take a sample, one from each of the populations, and compare those samples. And our null hypothesis it's typically going to be that there's no difference between the two population means. And if we're assuming the two populations have the same means, we would assume our samples then would be pretty close to each other. And here are your three options that you can possibly have for your null and alternative. The null always has equality in it. And you can either have a left-tailed test for alternative, right-tailed, or a two-tailed test if we're just checking for not equals. Let me look at the graph here. It's going to look similar to what we've been doing if both of our populations are actually, like our null hypothesis is assuming, if they are the same. When you would subtract the means from each other, you get 0 because they're the same mean. So we're going to have our sampling distribution is going to have 0 right in the middle, and we're going to look at our samples. And when we look at those sample means, we would expect when we subtract them from each other, that's going to be part of our test statistic. When we subtract our sample means from each other, it's going to be really close to 0, right in the middle, because we're assuming our null is that these samples are going to be similar because our populations are similar. If we check our samples, we do that subtraction, we get a test statistic that's way far out in the tails, just like in the past. That means we're going to reject our null hypothesis. So I'm going to look at the first problem here from the review homework. It'll help with the problems from 8.1. The mean exam score for 47 male high school students is 21.5. So we have a sample, and we got our sample mean. And we have the population standard deviation of 4.9. The mean exam score for 58 female high school students is 21.2. So this is our second population. Our second sample is the females, and we have our second sample mean here. The population standard deviation is 4.2. We get our significance level, and we ask if we can reject the claim that male and female high school students have equal exam scores. So first, let's set up our null and our alternative. Look at what the claim is. It's that male and female high school students have equal exam scores. So our null is going to be that the means are equal. Our alternative then would be that they're not equal. So jumping into Excel, I've copied down all the information from the problem. You're going to want to know what your null and alternative are. And then you have two separate samples. Get your sample size, the mean from each sample. And for these problems from 8.1, kind of highlighted it here, we know we're dealing with a certain situation when we know the population standard deviation. In 8.2, we're not going to have that, and we're going to change our approach a little bit. But when you have the population standard deviation, we're going to use the normal distribution, and we're dealing with the 8.1 content. So I've recorded the population standard deviations in my alpha. Now the rejection region I can get just like with previous chapters. It's all based off knowing that we're using the normal distribution, and this is my alpha, and I have a not equal or a two-tailed test. So I'm just going to do norm.s.inverse, my alpha divided by 2 to split the 1% between the two tails. So if my test statistics comes back further away from 0, further away from the middle of the distribution, out in the tails, if it's past either negative 2.57 or positive 2.57, I'm going to reject the null hypothesis. So now let me show you how to get the test statistic for our particular situation. And so here's the approach you're going to want to use. This is on page 421 from chapter 8.1. And we use it whenever both of our population standard deviations are known. We're going to be doing a z-test normal distribution. Here's our standardized test statistic. It's going to look a little more complicated, but it's the same basic format. You take your stuff from your samples, minus the population, and divide by the standard deviation to see how far away from the middle of the distribution you are, how far out into the tails you are. Now, this is going to be 0 almost every time because we're always assuming that our two populations are the same. That's our null hypothesis. So really, you're minusing 0 here. This part is based on your samples. And then you divide by our standard deviation here for our test statistic, and it tells you how to calculate it. So I recommend doing this part first, getting the value, and then you subtract your samples and divide by that value. So jumping back into Excel, it's exactly what I did. You need it for the standard deviation for your test statistic. You take the square root. Make sure you're doing, and let me get back in here to show you. Make sure you're doing the standard deviation squared, the variance divided by the size of the sample. The population variance divided by the size of the sample. So the problem gave me standard deviation for the population. I square that to get variance and divide by the size of the sample. So that squared divided by sample size plus the other population standard deviation squared, the variance divided by sample size. Add those together and take the square root. That gives you, that gives you your test statistic, standard deviation for it, and then for that test statistic, you just are subtracting the two means to see what their difference are, how far apart they are. We're assuming they're really close together. So yeah, that minus this part is just minus 0, so I don't even really do anything because minusing 0 doesn't change the value. So subtract the two sample means and divide by what you just got for the standard deviation to see how far away we are, how far out into the tails. Now this is much less than negative 2.57 or positive 2.57. It's in between those. And so we would not reject the null hypothesis. So jumping to 8.2, the concept remains the same. The main difference here is that we don't know the population standard deviations. We're still trying to find if there's a difference in the means between the two populations. So here we have a pet association claims that the mean annual cost of food for dogs and cats are the same. And then here is our sample information, and here's our alpha. And we're trying to look at these samples and see if it supports that the means are the same. So our null, again, it's going to be that the means are the same. Our alternative is that they're not the same. Let me copy this information into Excel. This would actually be for dogs now, and this here would be for the cats. And so the main thing, the way you know you're working with 8.2 is you're looking for means, but the population standard deviation is unknown. Instead, you're given sample standard deviation. And we're going to have to use that as we use our test statistic, and that means we're working with the t-distribution instead of the normal distribution. So one key thing you have to do with the t-distribution is find your degrees of freedom. So let me show you how you do that. So this is a chart in the textbook that's actually pretty useful. So we're working with the situation with the population and standard deviations are not known. We're in 8.2, we're going to be using the t-distribution. When we come down here, you need to know if the population variances are equal or not. And this problem actually says they're not. I'll go back and show you where it says that in the problem. But if they are, you're going to have this for your test statistic standard deviation. And this is your degrees of freedom. If they're not, you use this for your test statistic standard deviation and this for your degrees of freedom. And so our degrees of freedom is just the smaller of either the first sample size minus 1 or the second sample size minus 1. And our first sample size was 18, the second one's 8, so 8 minus 1 is 7. That's the smaller of the two. That's our degrees of freedom. And so based off our alpha rejection region, this is pretty standard now. Our t-test we're doing 2 tails, and so we just want our alpha in the tails and our degrees of freedom. And when you hit that, you get the critical values. So either negative 1.89 or positive 1.89. Those are the cutoffs for our rejection region. And going back to the problem to show that, it says right here, the population variances are not equal. And so we're going to need to find this. For our test statistic, it looks very similar to what we did in 8.1, but instead of the population variance divided by the sample size, we're going to use that sample variance divided by the sample size. And let me just scroll on down to show you the test statistic is actually looks exactly the same, where we're subtracting our sample means. This value is 0 because we're assuming our populations are the same, and then we divide by what we get for that sample standard deviation. So standard deviation for the test statistic, like I mentioned, we're just looking at what our samples came back for standard deviation. We square that, divide by the sample size, and add that to the same thing for our second sample, 28 squared divided by 8. And take the square root of all that. That gives us our standard deviation. Then we're going to subtract the means from each sample. And then you divide by that standard deviation for the test statistic that you just figured out. And that gives you then your test statistic. And this is much further into the tail past our critical value. So we're in the rejection region, and we're definitely going to reject our null hypothesis.